Attendees are in listen-only mode.
You're good anytime.
Good afternoon, everyone. Welcome to this webinar brought to you by the Pacific Ocean Education Team, or POET. Our goal is to enhance ocean stewardship efforts in the Pacific West and Alaska regions. My name is Bonnie Phillips, and it's my pleasure to host this webinar as a POET member and a park ranger at Cabrillo National Monument in San Diego. I want to thank all of you for joining us in our stewardship effort by participating in today's webinar. Before we introduce our featured speaker, I'd like to give a big thanks to Jim Pfeifenberger of the Ocean Alaska Science and Learning Center, and also to Dr. Sarah Allen of the Pacific West region for helping to coordinate this webinar series. I'd also like to welcome and thank John Morris from the Alaska region, who is here today to help moderate the technical aspects of our webinar. He's here now to explain how you can submit any questions you might have.
Thanks, Bonnie. That's great. Just to let you know, anyone who's new to the webinar process, it's pretty easy to comment or ask questions at any time during the webinar. You'll find at the bottom of your control panel a little question or chat box, and you just type a question in there, and it shows up for me and Bonnie to approve. And so if you have questions or difficulties, you can watch that question box for responses. We generally hold questions and answers to the end of the session, so but you can ask a question anytime by doing so. Also, just so you know, the webinar system is really stable, but occasionally we'll have high bandwidth other traffic on the line. So depending on where you are, you might hear the audio drop out intermittently. Just be patient; it generally comes back without any difficulty shortly. So any other technical issues, just let me know, and I'll turn it back over to Bonnie. Thanks.
All right, thanks, John. Our guest speaker today is Dr. Patrick Barnard. He is a coastal geologist with the USGS Pacific Coastal and Marine Science Center in Santa Cruz. His research focuses on the dynamics and evolution of California's high-energy beaches, with an emphasis on storm and climate change impacts. Thank you very much for presenting today.
Thanks, Bonnie, and thanks, John. Can everybody hear me okay? All right.
I hear you.
Great. Well, I'm going to talk about a project we've been developing with a number of different partners, including the National Park Service, in particular with a lot of aid from Jody Eshelman, and also support from Rebecca Beavers and others. And the goal of this effort is to look at the coastal impact of climate change on the California coast. And we've had a pilot project in Southern California, and now we're currently focused on the north central California coast. And there's a lot of motivation for this type of work. Certainly there's economic motivation in terms of the many billions of dollars that the California beaches contribute to the local, state, and national economy. But from a scientific perspective, we're going to focus mostly on the physical motivations, such as, for instance, sea level rise, of course, is going to place additional stresses on coastal systems worldwide, and that rate has increased by about 50% over the last 2 decades globally. West Coast sea level rise, however, has actually been suppressed for the last 30 years. There's been no recognizable sea level rise for really any of the West Coast tide gauges since about 1980. And this is because we've been in a period where prevailing wind patterns, predominantly out of the northwest, have actually suppressed sea level rise. This is sort of upwelling favorable winds. And this is something that Peter Bromierski recognized in a recent article in the Journal of Geophysical Research. But he also noted that these wind stress patterns that have been suppressing sea level along the West Coast may be relaxing, so we may be very soon returning to the background global rate of sea level rise, which is about 3 millimeters a year, or even higher rates. In addition to the sea level rise issue, there's also been a recognized trend of increased average winter and extreme wave energy for much of the West Coast. This is particularly evident in the Pacific Northwest, where the largest waves of the year have increased by as much as 3 meters over the last several decades, and less of a signal as you get more into central and southern California. But there's something going on with the wave climate, and this has also been noted in the cyclone activity in the eastern North Pacific Ocean over the last 50 years. Also, several climate models do suggest more El Nino-like conditions over the next century. And what this means for the West Coast is higher seasonal water levels and more extreme wave conditions. Now, globally, when we start to embark on a project looking at the impact of sea level rise, we're looking at the literature out there and trying to get a handle on what's the target, what are people looking at, what's the range. And this is kind of just a synopsis of sort of the highlights of what's out there in the literature. Of course, most people are familiar with the IPCC projections of about 20 to 60 centimeters of sea level rise by 2100. And these are admittedly very conservative because they don't include ice sheet contributions. And this was recognized in IPCC, and it's since been improved upon. Now that we know more about ice sheet dynamics, those contributions are beginning to be included in the latest projections. And this was the case with Ramsdorff and variations of the Ramsdorff work, where he took a new tact, however, and he related global sea level rise to mean surface temperature. He looked at this through the historical record and then projected it with the emission scenarios moving forward, and he came up with a range of about 0.5 meter to almost 2 meters of sea level rise by 2100. And then Tad Pfeffer at University of Colorado looked at much more specifically at ice sheet dynamics, and he constrained the upper end of sea level rise of 2 meters based on the most rapidly moving ice sheets in Greenland, and actually multiplying their rate by a factor of 10. And so he didn't see any physically tenable way to achieve a sea level rise of greater than 2 meters by 2100. And then Hansen at NASA, who's been in and out of the press quite a bit lately and over the last year, has suggested that 5 meters of sea level rise by 2100 is plausible. And this is due to what he calls nonlinearity of the coupled ocean-atmosphere system, and such as amplifying polar feedbacks, the so-called albedo flip, where snow and ice is highly reflective, but as you melt it, water absorbs heat much more easily, and therefore you're starting to basically have a positive feedback loop in terms of warming. In addition, he also argued that 50 million years ago, when we were essentially ice-free, sea level rise was 75 meters higher than today. And just 5 million years ago, sea level rise was about 25 meters higher, but we were only a few degrees warmer. But the higher A2 emission scenario from IPCC projects a temperature of about 4.5 degrees warmer. But I think most people agree that we will likely get to that level within several centuries, but that it's not possible given the feedbacks within the system and the rate that these changes move through the coupled ocean atmospheric system, that we could get to 5 meters by 2100. But we can kind of argue about these levels of sea level rise by 2100, but either way we're on a trajectory which is going to take us to multi-meter sea level rise levels in the next several centuries. And there's a new paper by Gevrajeva which actually looks at emission scenarios through 2500 and projects rates of up to 5.5 meters. Now this is a sort of a point at 2500 which is really only looked at in some types of municipal infrastructure such as sewage, and most of our planning horizons are more on the 20 to maybe 80-year, 90-year range through 2100. Now the global sea level rise signal is complicated by regional and local sea level variations, and this is a map showing sea level rise rates over the globe since 1993, when we began to have satellite altimetry, very accurate radar-based monitoring of the ocean surface. And this shows very significant variations in sea level. You see as much as 1 centimeter per year rise in the western Pacific, and then you can also see the suppression of sea level rise along the west coast, the eastern Pacific, due to regional ocean circulation patterns, wind patterns. Then on very short terms, there's also the impact of storms, and then there's also relative land movement, which can affect local sea level, particularly tectonics, isostatic rebound of areas that were once covered by ice sheets during the late Pleistocene, and also subsidence due to sediment compaction and fluid withdrawal. But overall, these trends moving forward are going to likely result in impacts such as accelerated beach erosion rates, a greater incidence of cliff failures as the toes of cliffs are more frequently attacked by waves. We're likely to see the landward translation of coastal flooding and inundation. More dangerous navigation conditions, particularly evident at harbor mouths. And beach and shore safety is likely to be more often compromised. Now, when we look forward at climate change and sea level rise, we also have to talk about extreme storms, because especially on the west coast, the real action happens when we have high water levels and very powerful waves. And this is when beaches are eroded. This is when flooding occurs. We're not going to, except in a few areas, and we're not going to see extensive flooding right away. It's going to be a slow and steady creeping of sea level rise. But if we have tens of centimeters of sea level rise coupled with a very large storm, that's when we're going to see major impacts. So in any modeling approach, we have to talk about extreme storms and the dual impact of extreme storms and sea level rise. Now, these are quite difficult to define because there's so many different parameters that can affect a storm and its impacts on the coast, and these include the wave height, which is in, of course, the energy therein, wind speed and direction, the atmospheric pressure. Wind speed, direction, atmospheric pressure contribute to the surge, the super elevation of water level. And we also have to consider wave direction, the duration of the storm, the prior beach state. Is it already at an eroded state, or is it a full summer, fall type of beach? And of course the water level. And on the right-hand side here is a plot of all the waves on a compass plot offshore of San Francisco over the last 15 years or so. And these bands are the wave height. And if you see my cursor here, this is the 8-meter band, about 25, 26 feet. Once you get outside of about 8 meters, things are getting pretty wild, and impacts are often quite severe for the coast. The largest waves recorded in this part of the coast in north central California are in the order of about 10 meters or so. But coincident with the wave energy, we then have to think about the elevated water levels that a storm can cause along the coast. This is what ultimately leads to significant impacts. So along the California coast, on average, the tide varies by about 2 meters. We can experience seasonal variations of local water levels by about 30 centimeters. This is especially apparent during El Nino winters when we have warmer water which expands. In addition, coastally trapped waves that move up the coast. And this can raise seasonal water levels by basically a foot over several months. Storm surge, basically the wind and the lowered atmospheric pressure during a storm, can raise water levels by 70 centimeters. And then wave setup, which is the super elevation of water levels within the surf zone due to wave breaking. And this can locally raise water levels by up to almost 2 meters during a severe event. So not even considering sea level rise, from a low tide to the height of an extreme storm, we can raise water levels along the coast by almost 5 meters, or roughly 16 or 17 feet. So if we're not modeling these processes, we're going to be missing the boat in terms of impacts of climate change moving forward. Now, along the north central coast, there's plenty of examples of areas that are already vulnerable to these kind of extreme water levels, not even considering any addition from sea level rise. And a lot of these areas are co-located with National Park Service lands, such as in the Stinson Beach area. This is out at Seadrift. I believe at the foot of this spit is where there's some National Park Service infrastructure. Already there's flooding here during storms. and sometimes quite significantly. The problems at Ocean Beach have been well documented. The city, just spent about $5 million shoring up the shoreline during the winter of 2009 and 10. This is an area that's been eroding for several decades already and threatening hundreds of millions of dollars of sewage infrastructure at present. Ocean Beach, of course, is owned by the National Park Service, GGNRA. In Pacifica, just down the coast a bit, significant cliff failures have been occurring for several decades, and several buildings were recently condemned again on the last El Nino winter of 2009-10 after significant impacts in the El Nino winter of 97-98. These are just a few examples. But so if we're going to build a modeling system to look at the impact of climate change, these are some of the essential features we have to have, taking in mind the importance of these storms as well as sea level rise. So most importantly, we need a very accurate, high-resolution digital elevation model. We need a very accurate DEM, not only for the modeling, but just as importantly to properly project the flood extent of these events. We also need to include all the relevant physics during a significant storm, such as infragravity energy or long waves. This is also referred to as surf beat. And this is sort of the quasi-periodic run-up of waves, usually on the sort of the period of about 50 to 200 seconds that you may experience during a storm. If you've ever been on a beach during a storm and not been wet and all of a sudden you're up to your knees or waist because a wave has run up, that's because of infragravity energy. This is basically a series of waves with all their energy being trapped in the surf zone and being expended at once. Then there's also wave setup and run-up. We talked about wave setup, and then run-up being the run-up of individual wave bores. Surge, of course, while we don't get the extreme surge that the Gulf Coast can get or the East Coast, Katrina on the Gulf Coast had a surge of about 8.5 meters. We can get surges as much as 1 meter in the northern part of California and about 70 centimeters in the Bay Area. And this can be a tipping point. And then we also need realistic forcing conditions and scenarios. Appropriate sea level rise scenarios like we just talked about. And these are getting better and better, and there's people beginning to put probabilities on these, but as I mentioned that previous slide, probably about 1 meter is the target with a range of roughly about 50 centimeters to 2 meters through 2100. And also we want atmospheric forcing, that is the wind and pressure fields from global climate models moving forward through 2100 to give us the most accurate projection and boundary conditions for forcing our models. And equally important are relevant products. All these things are great, but if we don't have products that our partners can use, like yourselves, then it's a missed opportunity. So we developed the Coastal Storm Modeling System. It's been in development since about 2008 quite vigorously, and been on the table for a few years prior to that. But it represents the first physics-based numerical modeling system for looking at hazards on the West Coast. It predicts coastal inundation, flooding, wave heights, beach erosion, and cliff failures due to the joint impact of sea level rise and severe storms. It uses Pacific Ocean scale atmospheric forcing from these global climate models to make predictions at a very fine scale along shore. Roughly every 100 meters, wave heights and water levels are predicted by the model, and these are extrapolated and projected inland using a digital elevation model with a resolution of 2 meters. So the on-the-ground footprint of the projections are just basically about 6 or 7 feet. And as I mentioned, we're using these GCMs as forcing to simulate not only the extreme events but also your everyday events. So you can look forward to a period like 2050 or 2100 and understand both what everyday conditions look like but also extreme events, which are going to do most of the damage. So version 1.0 was constructed as a pilot for Southern California and has been completed. And there are, I can point you to some websites after that and some Google Earth products if you want to play with some of the what we produced there. But it's very outer coast focused. The protected bays are not explicitly modeled, although flooding projections are extrapolated into those bays. Flooding is based on the maximum run-up, but there are a limited set of scenarios. There's a so-called arc storm, which was a hypothetical storm developed for the USGS multi-hazards demonstration project in collaboration with the National Weather Service to look at a 500-year rainfall event. It was not a coastal energy of recurrence interval of roughly 500 meters, but in any case, that was performed. And then we did a January 2010 hindcast, which was probably the biggest coastal storm we've seen in at least a decade. And then for some very simple sea level rise scenarios, we took that January 2010 hindcast and added 50 to 100 years of sea level rise per the Ramsdorff projections, basically about half a meter and 1.4 meters. This is kind of what the overall setup of the model looks like and how things feed into each other. At the top here, what we start with is a global WaveWatch 3 model. And this is the primary wave model that are used for almost all regional, local wave forecasts to some extent, or at least drive them. It's the most commonly used model really in the world in terms of wave generation and transformation across large ocean basins. This is nested into an Eastern North Pacific WaveWatch 3 model, and then in turn we keep increasing the resolution and making more and more grids until we're at a very, very fine scale. First, all of Southern California is modeled, and then 3 separate models are nested within that, and then 3 models within each one of those nested models. So we can basically increase our resolution from tens of kilometers at the global scale down to roughly less than 100 meters at the local scale. And this is done at the more regional scale using Delft 3D models of SWAN and flow. Now, coupled with this, there's also a tide model which comes from the Topex Poseidon satellite data that feeds into these wave and flow models, and that's one of the primary boundary conditions. And then there's also meteorological models such as the global forecasting system, which can be fed into these as boundary conditions to these models for basically looking at operational forecasts of coastal hazards, which this modeling system can also perform. But most commonly, these meteorological inputs are from general circulation models or global climate models. And then the final step is once we have a time series of water levels and waves brought to the very, very near shore, we then drive these cross-shore models, which called X-Beach for extreme beach, which simulate the wave height transformation, the actual flooding, and the beach change during severe storms. And in Southern California and same in Northern California, these are spaced 100 meters along shore. The outer boundaries at about the 10-meter bathymetric contour. And so for the Southern California work, there are about 5,000 of these individual models, which are actually giving us the hazards information on the ground. Now, when we started thinking about moving up to the Bay Area, there are other physical impacts, other considerations that we wanted to consider and that we were omitting for simplicity and also based on the manpower we had. But in addition to the regional factors such as the ocean circulation patterns, the storminess, and very large-scale tectonics, there are also these local factors which can be very important for looking at the vulnerability of the shoreline to climate change. In the Bay Area in particular, subsidence is a huge effort, a huge issue, and it's going to be central to the work that we're going to be doing in a project within the Bay. There are areas in the Bay, for instance, Treasure Island, where they were built with artificial fill and are subsiding at rates up to 2 centimeters per year. basically an order of magnitude higher than the global sea level rise rate. So if we're excluding subsidence, we're really missing a huge factor which can greatly enhance the vulnerability of parts of the shoreline. There's also minor amounts of local tectonic deformation on the order of half a millimeter to a millimeter per year. And then fluvial discharge and sediment supply changes from the primary watersheds can also cause issues moving forward, especially during extreme storms. If there's very large flows out of the Sacramento-San Joaquin Delta, this can greatly enhance flooding potential, particularly up the estuary in places like Sassoon Bay and the North Bay of San Francisco. And of course, there's also development and restoration going on. Whoops. Sorry, what happened there? Okay. Okay, so now in North Central Coast, we've developed Cosmos version 2.0, and this is a collaboration with NOAA, PRBO Conservation Science, and the National Park Service. It's called Our Coast, Our Future, or OCOF, and this is exclusively focused on climate change impacts to the San Francisco Bay and the outer coast. We did just receive funding from the National Estuarine Research Reserve to extend the work, which initially only included work along the outer coast, to include all of San Francisco Bay. But right now I'm mostly focusing on the outer coast, and this is a project that's scheduled for completion at the end of this calendar year. The work inside the bay has a timeline of an additional 2 years past the completion of the outer coast portion of this project. We're in concert with PRBO. We're developing a sophisticated product tool with emphasis on ecological impacts. The storm scenarios are developed using the latest 2013 IPCC radiant forcing scenarios. These are basically the new term for emission scenarios, and also the most up-to-date, sophisticated general circulation models or global climate models. The things that we're going to include here are going to be, which have not been included before in work either on the outer coast or in San Francisco Bay, include flood flows, and bay hydrodynamics are going to be modeled, including the depth of flow and the uncertainty of the flooding extents. Fluvial discharge is going to be added, and also wind forcing is going to be downscaled from global climate models. So within the bay, we can actually make waves and make much better predictions of flooding. Also, relative land movement is going to be included as well. So the first step, as I mentioned before, is developing a digital elevation model. And Amy Foxgrover just completed this, and this should be online and available for download if anybody wants it within several months. It has coverage in basically any area that could potentially be impacted by sea level rise, or even for a tsunami for that matter, over the foreseeable future. Coverage from about plus or minus 20 meters of mean sea level. It uses all the most recent high-resolution data sets, multi-beam bathymetry and LiDAR, and a lot of this was collected in just the last couple of years. The resolution is 2 meters, and this is about a 5-fold increase in existing DEM resolution. Vertical uncertainty is about 15 centimeters or so. And here's just a view looking at the Drake's Estero area. Now we have a seamless bathymetric and topographic surface. It's effective for in giving us great confidence in transforming waves across the inner shelf and across the surf zone, for simulating hydrodynamics accurately, and also just as important for projecting the extent of floods during these extreme events that we're going to be simulating. And now that we have a DEM in place, I'm just going to run through the most basic inundation scenarios. And these are just the bathtub scenarios that other tools provide, but right away you can easily identify areas that are vulnerable to climate change. This is the Bolinas area, and this is just a typical mean high water condition. But then as we step through, here's mean high water plus half a meter of sea level rise. And I'll just bump this up to 1 meter, and this does not include any physics at all from the outer coast from waves, but you're already seeing some flooding on the backside of Sea Drift and a bit along the Highway 1 corridor, and also a bit of downtown Bolinas here, and almost onto the main road that cuts through Bolinas. And then I'll just cut up to 2 meters of sea level rise, again excluding any physics, no storm surge included here, no wave setup or run up, and you can already see that flooding is really quite extensive on Sea Drift and Highway 1 and Bolinas. Now this is extreme high water, which was the levels that were approximated during the 82-83 El Nino and also the 97-98 El Nino, showing what flooding looked like then, again with no physics included at all. This is just information from a tide gauge. And then if we, I'll just bump through here. If we look at then extreme high water plus 2 meters of sea level rise, you can see the extent of flooding. And this is the kind of tool that NOAA is about to produce called the Sea Level Rise Viewer for California. I believe the San Francisco Bay portion is going to be completed this summer, and then the outer coast for the entire state of California will be completed in the fall. But now if we add some very simple physics, such as what it looks like during an extreme event, 2 meters of sea level rise, extreme high water, and then also the wave setup. And if we shift back here and then back to what the actual physics looks like, then you can see that this area is extremely vulnerable to future climate change and sea level rise, with the entire spit underwater and the entire Highway 1 corridor underwater and huge portions of Bolinas underwater as well. So just to reiterate, if we're not including all these different components of the total water level predictions, then we're missing the boat. This is just another sort of to emphasize that point. You know, of course, this is not to scale, by the way, but of course there's sea level rise, but then we also have to consider the tide difference, and especially the tide during an event. And then you have the wind and barometric setup, which is basically the surge, the wave setup, and the wave run-up. All this is also impacted by the beach slope and, of course, the wave direction as well. And looking at the bottom, these are just some shots from what I already showed you in previous slides. But if you did have just a bathtub model, this is what flooding might look like. And then if you include the physics during an extreme event on the right-hand side, you see much more extensive flooding. And just reiterating how critical it is to include all these physics in any climate change impacts model to get an accurate assessment of what's going to be vulnerable. So for our coast, our future work, we are developing a series of forcing scenarios to hopefully cover the full range of what can be expected through 2100. And this includes sea level rise of roughly 0 to 2 meters in 25 centimeter increments. And we're also going to include one extreme scenario per the Hansen work. The tide will be the mean high water when we're looking at non-storm, sort of everyday conditions, and otherwise we'll be doing a joint probability analysis between the tide level and the timing with a storm. For wave and storm conditions, we're looking at average conditions, annual extreme events, and also the 100-year return interval extreme event. And these are all based on a wave time series ensemble that we've are currently running right now, actually, from a suite of global climate models. Preliminary scenarios have been completed, and currently we're working up the full suite of scenarios, and these will all be completed by the summer with the project done by the end of the calendar year. As we are building these scenarios, PRBO is developing the user tool and beginning to beta test that in just a couple of months. And this is just an example of showing what the grid structure looks like in the San Francisco Bay Area and how we've improved this over Southern California is that now we've nested lots of small models in areas of importance, especially protected bays, so we can explicitly model the hydrodynamics in these bays themselves. And this is probably better illustrated here. We have all these regional and local model grids, and then these very high-resolution grids in areas in protected bays and also areas of heightened management and agency interest, such as Tomales Bay and Drake's Estero, Bolinas, Muir Beach, all National Park Service areas, Ocean Beach as well, Lindemar and Pacifica, and also Pillar Point Harbor, right near Mavericks Surf Break. And just finish up here with a few examples of the products we developed for Southern California in that pilot project, and similar efforts are going to be done, but in a much more sophisticated user interface for Northern California. As I mentioned, PRBO is developing. But this just shows flooding in the Del Mar area from this so-called arc storm that we looked at, and then projected flooding from the January 2010 event. And then to emphasize how important how much things are going to change moving forward, here's the extension of flooding, projection of flooding, adding 50 years of sea level rise to the January 2010 event, which is really an event that happens about every decade. So this is not a 100-year recurrence interval event by any stretch. And then if you add 100 years of sea level rise to that sort of decadal recurrence interval event, this is the amount of flooding that's projected by Cosmos. From sort of a space view, we wanted to develop a product suite where you could easily identify areas in a very large coastal stretch that are going to be vulnerable to a specific event. And this is just an example from this arc storm event. And the areas in red are areas that either have in this there's a small cliff failure pilot project that was going on. But these red squares I want to focus on now are areas where the waves are very, very large and have high damage potential. So from this satellite view, right away from the Southern California Bight, you could go in and say, okay, these oil platforms in the western Santa Barbara Channel are vulnerable, as are west-facing beaches in Los Angeles and northern San Diego County. Now, zoom in on an area, and this is an example from Imperial Beach in the Tijuana estuary. There's much more detail at this scale. This band shows the predictions of shoreline change during this particular scenario. And so in red is a very, very high rates of shoreline change. And these outer diamonds here are wave heights basically greater than 3 meters. And this is the case for all sites here. And then you also, of course, see the flooding extent projected from this event. And then you can also look at the actual precise location of where we predict the shoreline change will be in the course of this event. Another way of looking at this is in this view of all the cross-shore profile models that were performed during this scenario. And basically, we can go in here and zoom in on any area of your choosing. Let's say Silver Strand here in Coronado. You can click on any line you want and get a ton of information about what happened during that particular event per the model predictions, such as how large were the waves, how high did the water level get on the beach, how much did the shoreline change, and on, including flood duration. In this case, it's how often the back beach was underwater, or what was the time of that. In this case, it was over 50 hours. And then there's also the position of the profile, the beach profile before the storm and after the storm. And there's also, you could click on a link here to look at a movie of how the wave heights during the storm and how the profile changed as well. But given that we're on this webinar, I didn't think that would look too good. Now, the path forward. Cosmos is currently used to assess coastal vulnerability to climate change in this OCOF project in partnership with the National Park Service and others. But we designed it to be easily adaptable as more sophisticated climate change models and predictions emerge. seems the sea level rise projections can change almost on a monthly basis, so it's very easy for us to make these changes and rerun the model. We'd like to expand to cover more or all of the West Coast, but it's also available as a real-time warning system for emergency managers, lifeline operators, and resource managers. And our partners at Delft, Deltaris in the Netherlands, are very excited to explore this, and we've been talking with folks like the National Weather Service and the Corps of Engineers at pursuing this particular aspect. But within USGS, our primary interests are looking at the impact of climate change on the California coast. So thank you so much for all your time, and turn it over to Bonnie and John to handle the questions and answers, I guess.
Very good. We'll do. A nice presentation. Thanks. So this is your opportunity, folks, to go ahead and jump in and ask questions. And we are getting some questions coming in. As they come in, we'll try to kind of feed them into the question box, so you'll be able to see some of the other questions folks are asking as well. And then Bonnie and I will kind of field them and prompt them to Patrick so we can respond to them. So given that, we'll go ahead and start. We have a question from Matt Holmes, who asked, how will education folk get their hands on these scenarios once they are complete? I'm guessing you have the websites and information for that, Patrick?
Yeah, and actually one of the main thrusts of the Our Coast, Our Future project, and one of the great benefits of working with PRBO Conservation Science and NOAA and the National Park Service is that they're developing a user tool in collaboration with coastal managers in the region that will be, it's being beta tested. It's going to, a lot of time and effort is going into making that something that's easily available, easy to use, and easy to distribute. So its outreach is really almost half of this Northern California effort. The other half being the scientific development of the model.
Very good. Bonnie, you want to take the next one there?
Sure. Have any projections been done for inside San Francisco Bay, particularly places like San Francisco Maritime, Richmond area? And that's from Sue Fritzke.
Sure. Well, NOAA Knowles has done the most sophisticated flooding projections for San Francisco Bay to date. That was completed, I believe, in 2009, and that information can be found on the web. Our modeling has not yet made projections for the future for San Francisco. We'll probably begin doing that for the bay itself. Right now we're just focused on the outer coast, but we'll start to have those kinds of results probably coming out in about a year or so. But the NOAA Knowles work is a very good first approximation for any bay flooding.
So we have another question from Yvonne Barnard here asking, are the DEMs available for Southern California, specifically Santa Barbara Channel? Are there any?
Yes, yes they are. If you just search for my name and digital data series, you'd be able to find them. Or you can email me and I can send you a direct link. They're available, I believe, as ASCII grids for all of the Southern California coast.
Okay, we have another question here from David Cannon. Was the model calibrated and validated for various storm events?
Yeah, very good question. We've been doing extensive testing of the model, especially in Southern California, using a lot of the scripts data that they have for beach change. It's one of these. Some of this data is very hard to come by. There's a few data sets. We have extensive coastal change data with fine enough resolution at Ocean Beach in Northern California, so it's being extensively tested there, and it looks pretty good. The stuff in San Diego has been even more extensively tested, and that looks pretty good as well, but that's just for a coastal change, basically beach change during a storm. The extent of flooding, those kinds of data sets rarely, if ever, exist. Unless there's like a Hurricane Katrina type of event, it's pretty uncommon for anyone to have sort of digital information, anything beyond anecdotal information about areas that are flooded. Anecdotally, we know it performs quite well during the Southern California testing, and there is one site, we were very fortunate, Newport Harbor, the city of Newport actually went out and took pictures of a flood in 2005, and so that's been our primary flood data set. We've actually been able to make a quantitative comparison between the flooding we project and what actually happened on the ground. Brett Sanders and one of his students, Timu Gallian at UC Irvine, took those photos, went out with a handheld, or with a survey grade GPS, and got real world coordinates for them. And so that's been our primary flood extent data set, and so far the model is performing quite well. But this is always an issue with these kinds of projections. There just aren't data sets that are available with any great, especially regional extent. And so usually it's very, if anything, it's very localized information, often anecdotal, that you have to use to calibrate and test your model.
Okay, Patrick, here's a real kind of more specific request from Chris Webb. He's asking, we need to be able to see the Southern California results for the January 2010 storm. Is there a link for the results for that?
There is no link, but if you send me an email, I can send you a KMZ project, and you can pull it up in Google Earth and look at it. And I'd really appreciate anyone who has any feedback on those projections, if they have sort of experience on the ground, to let us know if they feel it's performing well or if there are areas that we're missing altogether.
And your email address is right there on the screen too. Great.
Yes.
Okay, there's another question of any chance we could get copies of this PowerPoint. I can tell you that this will be posted on a website, oceanalaska.org, and I will be reading that website again at the conclusion of our Q&A session here. As for downloading it, though, I don't know, John, maybe you might have some more technical background on that.
Yeah, we should be able to post both the PowerPoint in a PDF form and also a recording of the session today on that site. So stay tuned for the post-webinar email on that. Next question here from Carolyn Shoulders. In general, how would you summarize the relationship between the IPCC projections for sea level rise and your model projections?
Sure. Well, we haven't ourselves modeled sea level rise. We take other projections and we incorporate them in our model as a boundary condition. But I've been pretty involved in the climate research literature over the last few years, and everyone I've ever talked to believes that the IPCC projections are extremely conservative, and the primary reason being that, which we mentioned, that they don't include any melting of ice from Greenland or Antarctica, which is a huge factor. And so while IPCC has an upper limit of basically 60 centimeters by 2100, which they're going to probably be updating perhaps significantly in their 2013 report, which is the 5th assessment. Most climate scientists, even ones within IPCC, believe that we're going to get at least 1 meter of sea level rise by 2100.
The next question, are there plans for future modeling and or current data available for the, quote, real Northern California north of Point Reyes, from Susan?
Absolutely. We'd like to do that if we can get funding to do it. We are going up to the Humboldt Bay Symposium in April, and we'd be very interested in extending the model up in that direction. We are talking with tribes also at the Klamath River mouth, a little bit further north there, about moving the model up there. It's transferable. It's not a major effort to do so because most of the infrastructure has been completed, and all the scripting and coding and stuff that goes into this, it's easily transferable. This has to be a little bit of ramp-up time for getting bathymetry and topography, but we would like to do that very much. We're just looking for funding.
Along those lines, Patrick, do you know if there's modeling of that nature that's available for the Alaskan coast or further up the west coast?
I'm not aware, but we do have an Alaska project now, which is looking at some of those issues more in like a physical or like sort of a process-based approach from looking at what's happening today. And Lee Erickson has been doing modeling on the North Slope, and she is probably the best contact to if you want to discuss more about Alaska coastal change and impacts.
Great. So here's a question from Vicky Azaki. Will sand berms, in other words sand spits, grow higher or keep pace with increasing sea level rise or be inundated over time?
Yeah, that's a great question. Certainly there's going to be some in areas where there is room to migrate, and most of our areas are kind of cliff back to Northern California and Southern California. It's so highly developed that these beaches are getting pinched out one way or the other, but certainly there's going to be some evolution of the shore. The berms are going to have to, the beach is going to be translated landward and higher, but there has to be enough sediment available to do that as well. And based on the amount of damming and impoundment of sediment moving forward, it's unlikely that there's going to be a huge enough sediment supply to have a naturally protective beach that's going to be able to sustain the dual impact of sea level rise and climate change. One thing that we are not including in our model is sediment supply, and that is a big unknown, although most trends, as I just mentioned, are for a reduced sediment supply through time.
It looks like there is a question about one of the links and possibly not working, so we will look into that here with Dr. Barnard after this and address that so that you can get to that information or get to where you are looking to go. We can go down to the next question. You mentioned Google Earth plugins or products. Is there a way to look at these models, change their parameters to create new ones on Google Earth as of right now? That's from Bradley.
No, there isn't. But one of the main aims of the OCOF work in North Central Coast is to create a extremely dynamic user interface where you can choose from maybe basically dozens of scenarios. You pick your sea level rise. You pick the type of storm. Is it an annual one or a 100-year type of storm? And then then you'll be able to view the projected impacts of that particular storm in terms of particularly flooding extent, but also projected rates of erosion and some other factors which are likely going to be linked to some ecological data sets that we are getting from PRBO and the National Park Service and others. So it's going to be a more dynamic interface where you can actually choose from a number of different options instead of just sitting there and looking at a Google Earth project and not really having, and what it is what it is. So in the next iteration, the user is going to be in more control.
Patrick, you mentioned PRBO a couple times. I'm not familiar with that acronym. Can you explain it?
Yeah, Point Reyes Bird Observatory.
Okay, just confirming. Good.
Yeah.
I'm in Alaska. I'm excused, okay. So another question. We've got room for one or two more questions here. So here's one from Fernando Bilaba. So far, how have local governments or resource managers applied information from the model?
Yeah. There hasn't been, I think there's going to be a lot more traction here in North Central Coast, especially because we're choosing our scenarios very specifically to look at the range of impacts from climate change. And so there's been we've had a couple of workshops with I think about a total of about 80 local, regional managers, cities, counties, federal agencies, etc., that want to use this kind of information moving forward, and so that's why we're getting their feedback. But as of now, I think people are just kind of looking at these results and saying, okay, that that doesn't look good, or this area we have to start thinking about this, and that's what most people are saying is, okay, we have to start thinking about this now. We've seen the results, but it's difficult to see any tangible activities that have been going on in response besides a greater awareness at this stage.
Looks like we're running out of questions. Patrick, any final comments before we wrap up?
Looks like, yeah.
Not for me. I mean, just thank you so much for the opportunity, and it's been a really great partnership with the National Park Service in developing this system. And you know, one of the near-term goals is to apply this to you know, as many Park Service shorelines as possible. Probably the next major one outside of the north central coast maybe would be the Channel Islands.
All right. Well, thank you very much, Dr. Patrick Barnard from the USGS. Thank you, all of you, for attending and for your excellent questions. If you have submitted a question that we happen to miss, Dr. Barnard has offered to respond via email at a future date, so we'll get any of those to him. We also want to mention that this webinar, again, will be posted online, as are all of our previous webinars. That website is oceanalaska.org. Again, that's oceanalaska.org. That is the Ocean Alaska Science and Learning Center website. The next Pacific Ocean Education Team webinar is March 15th with Dr. Daniel Pauly on fisheries decline, and we hope you can join us then. Thank you very much.